All right, so Stephane Dugowson from SUPMECA is going to tell us a little bit about interactivity.
Thank you. I first want to thank Spencer Brainer for this invitation. And in the next 10 minutes, I will try to give you an idea of the general theory of interactivity I've been developing for years. So I won't have much time for jokes. So let's begin right away with recalling the rules of the Conway Games game of life, which will be our guiding thread. Okay. So on an infinite plan grid, if a cell has exactly 3 alive neighbors, it will be alive at the next generation. If it has exactly 2 alive neighbors, its states will stay unchanged. In all other cases, the state of the cell will be 0. Here you can see an example of 2 successive transitions from a simple initial state. As a discrete dynamical system, the game of life can be seen as a functor alpha from the additive monoid of natural numbers to the category of sets with suitable state set and transition function. Notice, by the way, that the class of discrete dynamical systems constitute a topos. And let's now consider another model for the game of life. In a way, the simplest possible global model, we'll call it the one-step model. It consists of taking as domain of the functor a category with only one non-trivial row. And we keep the same rule of evolution. And so it is very simple. The one-step model represents a break with previous conceptions in which the domain category has to be a monoid. Madame Eresman seems to have been the first to consider this generalization in 1965. So for us, a dynamic or a functorial dynamic will be a functor whose domain will be called the engine of the dynamic. The rows of the engine will be called durations. In view of interactivity, more precisely in view of synchronizations, we need to add special dynamical systems we call clocks. And transformations from the considered dynamics to the associated clocks we call datations. The states of the clock will be called instants. For example, there is only 2 instants in this one-step model of the game of life. The instant 0 and the instant 1. Given a dynamic endowed with a clock, we'll call solution or realization of it any transformation from the clock to the considered dynamic such that the datation following the realization is included in the identity of the clock. By the way, we don't ask a realization to be a total function, but only a partial function. So realization can stop at any time. Therefore, the codomain category will not necessarily be the category of sets. Okay, now let's consider an individual component of the one-step game of life, that is a cell, as an open dynamical system. The openness is given by a dependence on a parameter. Thus, the state transition is now given by a family of functions indexed by a set L of parameter values. Here we took as L the set of possible numbers of neighbors of the cell, and the transitions are those that naturally arise from the game of life rules. To become a synchronizable dynamic, alpha has to be on the way with the clock. And now let's introduce a major generalization by replacing the transition functions by non-deterministic transitions, that is, functions which associate with each state a set of reachable states, will not big P, the category of sets with non-deterministic transitions as arrows. We could now imagine different non-deterministic rules depending on the lambda value, replacing the engine of a one-step cell by any small category. We get now the definition of an open functorial dynamic that is given an non-empty set L of parameter values, a functor into the category with L families of non-deterministic transitions as arrows, endowed with a clock that is a deterministic dynamic on the same engine. Then a realization of such an open dynamic will be given by some value of the parameter and a partial functional instance satisfying the same properties than previously. And let's now consider what we'll call interactive families. We'll define an interactive family by undergoing a family of open dynamics with synchronization and in interaction. Given a family of open dynamics, we define a synchronization by the choice of a conductor, so-called a metronome, or if you want a pacemaker, that is an element of the index set, and a family of monotonic maps from the instance of the conductor's clock to the instance of the other clocks, with certain properties I won't detail now. A family of open dynamics being synchronized by a conductor, we define an interaction between those dynamics as a multiple between their realizations and their parameters. For example, we can define a relation between an infinite family of individual open cells for the one-step game of life, taking as multiple R the one given by the graph written here, which expresses that parameters values have to be given by neighbors realizations at the instant 0, and the realizations have to be compatible with parameters values. So, you could be surprised that for us, parameters are linked not only with states, but even with realizations on the concerned dynamics. To understand this fundamental point, let's consider the interaction between a spring and a human operator who freely exerts a force on it. These are the equations of the movement of the spring, and this is the solution depending on initial conditions, of course, and depending on the force exerted by the operator from the initial instant until the future instant t considered. It means that, in general, with the exception of particularly interesting situations, the future will often depend on the future. In a paper posted on Archive in May 2015, I defined what I call the connectivity structure of any multiple relation. So the interaction between some dynamics give rise to some connectivity structures. For example, in the one-step game of life, those two cells are connected because the number of their neighbors are not independent. We'll see in a moment a less trivial example of connectivity, that is a Borromean one. But now, to any interactive family, we naturally want to associate a global open functorial dynamic. We can do this by defining the transitions of such a global dynamic from realizations of its components. But it appears that in general those generated dynamics are not functorial, but only what I call sub-functorial. Technically, this can be interpreted as a kind of lax functoriality. More precisely, sub-functorial dynamic alpha has to respect those inclusion properties. These properties have an unexpected repercussion, that is the fact that we now can design open timeless dynamics, because the transition associated with a zero duration can now depend on a parameter. Note that the timeless dynamics is useful to obtain some examples. or counterexamples. For example, taking 3 timeless deterministic dynamics, then we can see as some zero-step game of life, individual cells. We can consider the interaction with the interaction so that at least one of their realizations is alive, and this is a Borromean interaction. Okay. Yes. Anyway, with subfunctorial open dynamics, we have now a general system theory because any interactive family of subfunctorial open dynamics generates some global subfunctorial open dynamics. Of course, the dynamics generated by an interactive family are usually open, so they can enter in other interactions. And in conclusion, the theory of open subfunctorial dynamics is a language to describe and imagine many kinds of interacting dynamics, each with its own temporality. For example, we can imagine many temporal variants of the game of life in which some cells could have continuous time, cyclic time, multidimensional time, non-monoidal time, free will, etc. And well, it would be interesting to study the connection with some other theory concerning open systems, like the ones developed by David Spivak and others. And but I would say that some connectivity aspects will still have to be developed, and in a way, it's just a beginning. And you will find some references on the slide. And thank you very much.